I will expect all of you know. So basically the gauge theory and all those things, you are familiar with that language. And also the path integral formalism. Okay. Because I will not derive those effective action and all those things, I will rather use them. So first two lectures or 1.5 lecture will be based on to create the platform of the effective field theory, rather the language of the effective field theory, because effective field theory itself is a language that you need to understand first, and based on that we will do that thing. And the topics that I'll cover mostly based on 3 pillars. Okay. First is, I'll go into detail later, which is called the bottom up approach. Okay. So there you will see that if based on the symmetry and the knowledge of the quantum fields, there I will less use physics, I will mostly use the mathematics there. Okay. So this approach will be heavily dependent on the symmetry. Okay. There's another aspect of effective field theory which is not so effective field theory, which is called the top down. This will be more EFT driven. Okay. And then there's another approach or understanding the effective field theory, which is called the unfolding. Okay. This is an application of symmetry plus EFT plus experimental data. So these are 3 pillars of the effective field theory, and if you know one of them, that gives you a very incompleteness about the effective field theory. You cannot really use them. You can certainly blabber about the effective field theory, but in real practice, in the calculation or to make some significant work, you cannot do that thing unless you do understand all these 3 different aspects of effective field theory. Okay. So now the first question is basically, why effective field theory? Okay. The only and genuine answer is basically there is no theory of everything. What does it mean? That means physics is a phenomenological subject, okay, and we use basically computer, maths and all those things to understand and describe those phenomena, but it's mostly experimentally driven subject. Now whenever there's some kind of experiments are going on, okay, so that means basically it has some kind of scales involved there. Okay. Now this is one of the inherent property of the physical principles, that whenever we propose some kind of physical laws and that thing, there is some validity of region of those laws. For example, you start with the classical laws. Okay, they are valid in certain regime. You have this quantum mechanics, there is some valid regime. Okay, if you go beyond that, quantum field theory and so on. Okay, there is certain length scales are there. Now, as I suppose all of you know, so in the natural unit choice, these are very interesting relations that we have, that length and time are equivalent and they are related to mass inversely. Now what does it mean? That means basically if you have to probe a smaller length scale, you have to have a very high frequency light. Right? It's like so all these experiments are like a microscope, you can think of that way. Okay. So now that means when you talk about the very high energy, it's basically you are trying to probe a smaller length scale, okay, and vice versa. So this tells you now whenever I talk about the scale, that can be either I is talking about in terms of length scale or energy scale, that will be equivalent. You can map through these relations. Okay. But in this course, I will prefer mostly talk about the in terms of energy or the mass scale, but you can certainly connect that thing what the length scale what we are talking about, right? So now, because we do not have any kind of experimentally verified theory which is applicable across all the energy scale, okay, there is no such theory. Okay, there are proposals and all those things I don't consider as a physics laws unless they are proven in the experiments. Okay. So if you see we need to really focus on particular length scale. And when we do that, we need to focus on what are the degree of freedom floating around that length scales. What does it mean? That implies that, for example, let's say, are you familiar with this unit? GeV, right? It's a giga electron volt, which is equivalent to 1 proton's mass actually, roughly, right? Like 935 MeV, so that's roughly 1 GeV. Yeah, so because I will be using these units again and again. Now let's say if I have some experiment which is performing around, let's say, 10 GeV to, let's say, 100 GeV. Okay. Now, of course, there is some degree of freedom within this range. When I am talking about the degree of freedom, of course, I am talking about the on-shell degree of freedom. Okay. What do you mean by the on-shell degree of freedom? That if you really perform some kind of experiment within this energy, the rest mass of those particles are basically such that you can reproduce them on shell, and that means p square equal to m square. That relation you can satisfy. Okay. So when I talk about the fields, talking about the degree of freedom in this effective field theory context, I consider only the on-shell degree of freedom. If I am not explicitly mentioning them, it's always on-shell degree of freedom. In certain cases, I'll talk about the off-shells and all those things where I'll explicitly mention the off-shellness of the theory, right? So now let's say there are some kind of particles, and for example, as you know, for example, Mz, Mw, these are the particles which actually lie in this range, that you can produce the masses within 80, around roughly 80 GeV, 90 GeV and so on. So these are in range. But if my experimental reach is maximum 100 GeV, and then there are some other degrees of freedoms are also there, other kind of particles which you have discovered. For example, let's say top quark, which is roughly 170 GeV. Okay, you have a Higgs, which is roughly 125 GeV and so on. What about those particles? Because those particles are actually physical particles. But when you actually perform this kind of experiment, these particles cannot appear on shell. Okay. Now the question is how I should approach any kind of field theory calculation within this domain, right? Can I just state forward whatever the on-shell degree of freedom I have, I just use them to perform the scattering cross sections and all those things, forgetting everything about them? Or even if I want, I cannot include them in my calculation directly, right? So that means whenever there is some chunk of or ranges of energy scales are there, and we are focusing very precisely in that particular domain, okay, that's what the effective field theory help you to do that. So effective field theory is a more generic version of the quantum field theory, which help you focusing and understanding the physics for a particular domain. That's why whenever I talk about the effective field theory, automatically there is a concept of scales come here. And what are the scale? That how long that theory is validated. For example, if I construct effective field theory, let's say within this domain, certainly that theory cannot be extended beyond 100 GeV. Similarly, if I have to do something, if I have to stretch this, let's say 100 to let's say 200 GeV, what I have to do? You can see what are the existing degree of freedom I have between 10 to 100 GeV. That set of degree of freedom is increased because now these particles can be appeared on shell. So you can see the theory has changed. The theory has now additional degree of freedom. Now additional degree of freedom means additional interactions and so on. So that means I have a, let's say, two theories between 10 to 200 and another 10 to 100. The difference is basically between wider range of the energy scale, I can incorporate more and more degrees of freedom, higher, heavy degrees of freedom. Okay, because the lighter degree of freedom are common for them. The only difference basically the heavier beyond 100 to 200. Okay, so I can have a quantum field theory here, I can have a quantum field theory there. But as you can see, is there any smooth transition of the theory from 10 to 100 GeV to beyond 200 GeV. That's what the effective field theory help you to do that. Now, how you get these two approaches from this example? Let's say I do not know what are the degree of freedom. This I do not have any knowledge a priori. I can only have knowledge if experimentalists provide me that thing. Otherwise, I cannot have the knowledge. So I have all the knowledge about the degree of freedom and the symmetry at 10 to 100 GeV. Okay, but what I can see that there are some degree of freedom which are not within 100 GeV but beyond 100 GeV, but they may leave an impact in the interactions happening in this range. So if I don't really capture them and my experimental results are very precise, what I'll find out that if I rely only on the renormalizable interactions using the degree of freedom here, and if I calculate some kind of cross section or decay with some kind of observables, that will certainly mismatch with the experimental results. Because when you perform an experiment, it doesn't matter how do you compute, it just give you a raw result. Okay, it's our duty being a theoretician to map and model that thing. So that's where the revival comes through the approach one, bottom-up approach. What does it tell you? It tells you, okay, you know the symmetry and degree of freedom here. You write down the renormalizable interaction. Renormalizable means naively or superficially you can think of at this point, for example, let's say if you're working in a 3+1 dimension, you write down all the interactions which are basically up to mass dimension 4. So all your couplings have a mass dimension either greater than 0 or equal to 0. It's not less than 0. Okay. So now what you can do using the symmetry principles, what you can construct? You can construct higher mass dimensional operator. For example, dimension 5, dimension 6, because as I said, naively I'll always keep in mind that I'm working in a 3+1 dimension. So dimension 4 is basically after the renormalizable interactions. Beyond that, I'll add some higher mass dimension operator, dimension 5, dimension 6 and so on. And what are the coupling dimension of them? -1 for dimension -2, right? So I can call them, for example, C by lambda square in this way. C is just a dimensionless quantity, some number. So these kind of, so what I can do, I can add this kind of operator. Let me call it dimension 5, this is dimension 6 and so on, using the symmetry and this thing. And keep in mind, when I'm constructing these operators, the constituent of those operators are basically my all on-shell degree of freedom, and that I know in this range, but I do not know. But what I'm doing, as if I am capturing the footprint of those modes which are beyond 100 GeV, okay, but still I'm capturing their passive off-shell presence through these higher dimension operators. So effective field theory gives you a provision to capture the footprint of some unknown physics, okay, through the incorporation of the higher mass dimension operators. Okay, so that's what the bottom-up approach gives you. Now you can see that once you add this thing, so whatever the cross sections you have additional contribution from these operators, and then you can fit those C prime and C and then find out, okay, what is the strength of these additional couplings such that you can explain those data. Okay, so these are called the effective operators, and the accompanying coefficients have a special name which are called the Wilson coefficient. Okay, so now it may appear at this point, okay, if I know the symmetry, so I know the representations of the fields, because that's how you write the Lagrangian. How to write a Lagrangian? That you know the representations of the quantum fields, okay, and you try to do Young diagram technique, find out what are the singlets under individual group, and you write down this thing. But it's not that trivial. The reason is basically twofold. One is, when you are writing these operators, you have to be careful. You must create an operator basis. And when I'm saying this word basis, it is having the same mathematical interpretation as in the quantum mechanics, that there is no redundancy. So when I'm saying the Hilbert space, let's say 10 dimension, that means there is a 10 dimension vector space. If I draw another beyond something, I should be able to write down that vector in terms of other. For example, in 3 dimension, if you write down I, j, k unit vector, you can write down any other vector in terms of I, j, k. So similarly, for every mass dimension, there will be some operator basis. Okay. So now the operator basis means basically it is the number of counting and number of construction of the operator has to be exact. If I have a, let's say, 50 dimension 6 operator, it's always 50. It is not 51, it is not 49. So if you write down just, by Young diagram technique manually, you will make certainly mistake, because the number of operators exponentially become larger and larger when you go for higher dimension, because the possible contractions are more and more, right? So that's what is a non-trivial thing to do. And not only that, even sometimes we may write down 2 operators which may appear different, but they are not different through 2 things. One is basically equation of motion, okay, because these are on-shell degree of freedom, so they have a equation of motion. So if 2 operators are related to each other by the equation of motion, they are not independent. You just pick one of them. Another is, when you construct these operators, they are part of the Lagrangian density. And Lagrangian density is basically blended with an integral form when you write down the action. So there is a provision to perform in the space-time coordinate the integration by parts, right? So that means if 2 operators are related to each other by the integration by parts, then I cannot call them independent. So we have to formulate a mathematical technique such that we can guarantee and make sure an exhaustive list of operator bases. And we learn that, and that's what the mathematical technique called Hilbert series. So Hilbert series, yes.
What we do, okay. The addition of operators to match the experimental data, this is the same thing as renormalization, right?
No.
This is not the same thing.
Because when you do the renormalizations, you basically restrict yourself to the same number of bare operators, right?
As in here,
for example, you have, let's say, 5-4 theory. Okay, you don't, when you do renormalize the theory, you don't include the 5-6, 5-8 operators. What you do basically, the scale dependence of this coupling, how do they evolve with the scale? That's what the renormalization does. Okay, so that is not the same. That is basically the off-shell effect of the same degree of freedom that the quantum corrections you are doing in the renormalization group effect.
No, if you think about it from a Wilson perspective, so there you generate all the operators.
That is the Wilsonian EFT.
Yeah, so
that is the Wilsonian EFT.
No, Wilsonian RG. So
okay, so there is a 2 things you have to separate out. The Wilsonian EFT and Wilsonian RG are the different things. Okay, so when you talk about the RG, if you do not know the degree of freedom, how do you incorporate that effect?
So I am assuming the degree of freedom here you mean is the field phi, right? So
the degree of freedom, I mean the on-shell degree of freedom,
which in say phi 4 is my phi field.
Phi 4, yeah. For the phi field is the phi, exactly.
Phi field.
Yes.
So you are asking us to add operators made out of this phi field to the Lagrangian,
yes,
such that my experimental observations match my calculated quantities.
Yes.
But to me, this seems just like Wilsonian RG.
No.
Because there,
so Wilsonian RG, when you do that thing, so basically you are getting confused about the Wilsonian EFT approach and the RG approach. So the RG gives you basically you have a process you are looking at, tree level, right? And then you are actually calculating higher order correction to that process. That is not the EFT. Because that's a non-local effective action you are computing. But when you talk about the operators, they are the local operators. Okay, so you have to extract the information about the local operators from the non-local process.
Could you repeat this non-local local
Yeah.
thing?
So basically, let's say you actually calculate let's say this is the phi 4. Okay, then I can draw this diagram. This is a non-local diagram. Okay, and then I have, let's say, this kind of process at the one loop level. They are non-local diagram. But what they do not do the EFT. This is not a EFT. Effective action and the effective field theory, they are two different things. Effective field theory, you have to, project out from the effective action. And that is the lesson we will learn in the top-down approach. So what you are calling is an Wilsonian effective action. Effective action means there is a common word effective, but that doesn't make it an effective field theory. Okay. So now, when you calculate this diagram, what do you calculate? You calculate effective action. And then you calculate the beta functions from there, like Karan-Simanjik and all those things we do.
Yes.
What does it tell you? It tells you basically this coupling is lambda, how the lambda of mu behaves. So that's fine. That's the precision calculation. But in the whole but here these objects are still basically phi. There is no new degree of freedom. So there is no concept of decoupling. Okay. So this is what we are calling, it's a Wilsonian effective action. What I am talking about the effective field theory, which are local operators. So that is hidden there. You have to extract that information. Okay. Yeah. Any other question? Yeah.
So in order to find out non-redundant basis, you said that we have to take in account IBP and the equations of motion, right? So where does field redefinitions come
Which
into this
definitions?
picture? Field redefinitions.
Yeah.
Yeah, so they also play a role in this case?
Okay.
In order to
Good question. So I will not discuss detail here, but at this point, if you work up to dimension 6, equation of motion and the field definition, they are equivalent. Okay. But that is more important in the top-down approach, not in the bottom-up approach. Yeah.
So I understand the logic of the upper scale validity for an EFT, but you are also writing a lower scale like 10 to 200. So what's the logic of the lower scale for an
Okay,
EFT?
so just to say that, okay, because sometimes as you work also that the lower cutoff means you basically the degree of freedom, which I'm talking about the fundamental degree of freedom, let's say below 10 GeV, they cluster together and give a composite object. Then the same EFT cannot be translated there. For example, if I'm talking about, let's say, Higgs or quark and all those things, but after a certain scale, if you go, you get pions and all those things. So I cannot directly interpret that EFT there. I need to consider different EFT there. So this lower to just keeping in mind that at beyond some scale, that those what you are calling as the degree of freedom may not be there at the degree of freedom, but some clustered object treated as a degree of freedom. So that's the reason actually. Keeping QCD in mind actually, effectively I'd say. Yeah, thanks for that question. Yeah. Any other question? Okay. So yeah, so as I mentioned, the Hilbert series is the method that we will learn. So that is the first thing that you will enter. Let me tell you, the bottom-up approach is actually and historically the notion of the effective field theory. With effective field theory introduced that way, that if I do not know the UV interactions and all those things, if I only know the infinite degree of freedom and the symmetry at the low energy, okay, and then based on that principle, if I write down those higher mass dimension operators which actually capture the footprint, and when I'm talking about the higher mass dimension operator, so when I talk about this between 10 to 100, okay, then the particles which are much massive than this thing, they will be effect here. So lambda is basically the scale which is basically you can think of the lightest of the heavy scale, because you can have let's say for example 170, 125. So here my lambda would be 125. So this is the lightest among the heavy scale kind of thing. Now the next question is if just the particle is massive than the 100 GeV for this reference, I can use the EFT? The answer is no. That's where the concept of decoupling comes into your picture. that I can actually use effective field theory, okay, only when the heavier particles are really decoupled from my theory. Now, what is the meaning of decoupling and how they are parameterized the decoupling? That's where the famous Appelquist-Carrazon theorem comes into a picture, and we'll talk about in which context we can discuss this decoupling. But one has to be careful. For example, if my 100 GeV is there, is the maximum range of the energy, and if something is 105 GeV or 110 GeV, that means I cannot integrate out 105 GeV. Why? Because if I integrate out, I get a series of this, and this series will not be convergent. So I can integrate out only those particles which are basically really in the decoupling limit. Now, how do parameterize them? They generally, broadly, I can say the two aspects which parameterize the decoupling. One is the mass of these particles, okay, and how these particles interact with the lighter degree of freedom. If their masses are very heavy, but if they are strongly coupled to the lighter degree of freedom, I cannot do that thing. So in other words, you can think of the new heavy sector mixed with the lighter sector very naively. Okay, so that's how you can parameterize. And now, because when we calculate something, we need an algebraic estimation of this naiveness of the decoupling, and based on that, what we have in this EFT, another language is called the truncation. That means I can write down the whole infinite series in 1 by lambda square, 1 by lambda square, 1 by lambda 4, lambda 6, and so on. Now, for what kind of theory, where to truncate that? That tells you how strongly or weakly coupled is your new theory, or how much heavier those particles are. Now, that's why for certain kind of observables, we may think, okay, just dimension 6 operators are sufficient, because it also related with the precision of the experiment. For example, the cross section we have, if I add the dimension 6 operators, then I can explain all those results. Okay, I don't need to really add dimension 8, because I just add them perturbatively. Okay, and if near future, after 10-15 years, if the precision calculation is improved and if you get more precise result, possibly you have to add them. This is one of the reason. Another reason, some of the observables actually appear to be affected at certain order. Okay, then we have to calculate that order. One of the nicest example is, for example, if you look at the neutral gauge coupling. In standard model you have this neutral gauge couplings, right? The neutral currents and all those things. So trilinear and quartic neutral gauge couplings, if you see, they do not get any correction from the dimension 6 operators. They get correction only from the dimension 8. So now, if there are some observables you are computing in association with them, so if you truncate at dimension 6 level, you may miss out their contribution. So what kind of calculations you are making, what kind of observables you are actually trying to compute, that also dictate you that which order you should work with. So precision, decoupling, and the truncation, that's how it works. Okay. So this is the bottom-up approach where we do that thing. Now, there's another way to look into that, which is basically Wilsonian way of looking at the effective field theory. But this is not actually effective field theory. Then why we should discuss this thing, and what is it actually? It is more like it's an effective way of doing the full theory calculation. And let me tell you why. For example, let's say I have a Lagrangian of, let's say, phi light and phi heavy. Okay, I am not putting any numerical number. Just imagine that this, to start with, I have a UV Lagrangian which contains two different kind of fields. One is lighter fields, one is heavier field. That means there is some kind of intermediate M is sitting there which separate out these two fields actually. That means if I restrict my energy to be order of M, I can reproduce phi L on shell. I cannot reproduce phi H on shell, and so on. So this is the separating scale. Okay, and these two, and for the time being, I'm assuming that okay, the phi h is heavier enough and weakly coupled enough such that I can use the effective field theory. My decoupling is basically valid. Okay, this is my all assumption. So now, if I know the Lagrangian, if I know the theory, then what we should do actually? We just do the whole calculation with this full Lagrangian. I get the whole result and everything, right? That's absolutely fine. And there is no harm in that thing. That is called the full theory calculations. Okay, so with the full Lagrangian, what I can do is called the full theory calculations, and they're absolutely fine. But another way what we can do that, as I told you, if those phi h, quality of phi h is such that it satisfied the decoupling, and when I truncate them, the truncation and all those things are convergent, if it is allowed, then what I can write down, I can write down an L effective which is functional of only phi L. That means, so this is what the top down approach does actually. It actually removes the phi h degree of freedom from this Lagrangian, okay, and now when you are removing something, of course that effect is there, that will be captured, right? So that effects are captured in this effective Lagrangian. Why I am calling it an effective Lagrangian? That means, let's say, what are the, if this is a UV theory and renormalizable theory, what is the interaction with the phi L maximum you can have? Phi L to the power 4, right? You can have that operator. But when I have this thing, then I have this phi L to the power 4 plus C1 by lambda square. Then I can write down phi L to the power 6 plus d square phi L to the power 4. Let me put it 1 by C1, C2, and so on. Yeah. Just for simplicity, that depends on the interactions. That depends on the interaction symmetry. Yeah, I mean there is no reason to avoid them, apart from the I will not gain out of that thing anything for my discussion. Yeah. Okay, sure. So for example, let's start with an example. This thing. Okay. So let's say I have a UV theory. When I'm saying UV complete theory means this is a renormalizable theory. Okay, it's valid across the energy. There is no issue with the unitarity and all those things. It is a perfectly fine, well-behaved theory. Then I found out, okay, so I do all the calculation, and that calculation I call it a full theory calculation. Right? Now, I notice that I have a 2 degrees of freedom in this theory, which is one is phi L, one is phi h. Okay, and then I want to perform a calculation of the observable at some scale which is much less than the mass of this heavy particle. That I am calling, let's say, let me call that a mu, and this is much less than the m phi h. Okay, so that you can see that if I am working in this kind of up to this energy domain, this appears to me this degree of freedom as an unnecessary degree of freedom to deal with, because if you have more and more degree of freedom, okay, because in real practice we do not do toy models, we do real models, and real models have a lot of interaction, gauge bosons, fermions and all those things. So that's why it becomes very claustrophobic environment to calculate something observable, realistic observable, right? So don't think that okay, what is the if I have a 2 scalar field, what is happening? Something very easy, but this is just a toy example. So now if I find that okay, this degree of freedoms on cell presence is not required, because it is so heavy and I am looking at a very low energy observers. So then what I can do, just to make my life simple, I just try to delete some of the heavier modes, which are heavier in a sense, much heavier than the scale where I am digging there, right? So then if I try to delete them such that real practice I have to deal with only a fewer number of fields. So now, how I can delete this thing? That tells you whether this particle is qualified to be decoupled or not. That means the phi h interaction, for example, one kind of interaction you can think lambda phi square, right? This is a quartic interaction, interaction. if your lambda is smaller, okay, if lambda is 100, you cannot do that thing. It becomes non-perturbative. A strongly coupled theory, you cannot just use the perturbation. But if it's a very small, let's say order of 1 or less than 1, then it's a weakly coupled theory. I can perform the perturbation, and then phi h mass is heavier than the mu. Okay, you have a question, Dipanshu? Okay. Then I can show algebraically that this satisfies the decoupling. Okay, that means if I decouple this theory, this object, okay, then I can rewrite this Lagrangian in terms of an effective Lagrangian, okay, which gives me the same answer up to a precision factor at this scale. That means if I do the full theory calculation, or if I do this effective field theory calculation only with this phi L, I will get exactly same answer up to a certain error, and that error is beyond the resolution of the experiment. So effectively from the experimental point of view, you find they are matching actually. But of course, these are numerical matching. Basically, it's not an algebraic 0 equal to 0 matching. You can understand there are some errors are there, but the errors are so small compared to the resolution of the experiment that they are ignorant. Okay, so in this kind of theory, we can take the advantage of the effective field theory top down. Why I am calling it top down approach? Because you know the UV theory at high energy. So top down is in terms of energy. You have a high energy, and then you integrate that out. That possibly decouple, which are qualified to be decoupled. Those kind of particles you can decouple, and that decoupling has a special mean. It's called integrating out. So you have to integrate out this phi h from the full Lagrangian, and in the process of integrating out, you generate this effective Lagrangian. Okay. Now the word integrating out, okay. So the question is there any kind of integrations is there? Yes, of course there are some kind of integrations are there. Why? If you remember the path integral, so basically you have this. You have a measure over the phi L and measure over the phi h, okay, and what you can do, you can perform the path Gaussian integral over this d phi h measure, okay, such that you live with the effective action initially in terms of the phi L. So when you do this integrating out, so basically when you say I am doing the integrate out, I calculate an effective action in terms of phi L. Okay, now the question is this gamma effective is just I can translate in terms of L effective? Answer is no, because this is what the effective action. This is still not the effective field theory. Why? Because when you do this, it is not only the function of the phi L, but it is also function of the phi h c. What is the phi h c? Phi h c are the classical solutions of the heavy field. That means right. So that's why you basically get the solution of that thing. And what kind of solutions you get from there, I'll go into more detail and I'll show especially how to do that thing. But as I told you, first 2 lectures will be to set up the environment for the effective field theory and to clean your mind that you have gathered already wrong things in your mind. So now, if you see the phi h c roughly looks like let me call it, okay, let me put some del square minus m squares plus some function of phi and then some function of light fields, right? So this is the, if you solve the Euler equation, this is because these are scalar fields, so this is the quadratic plane Gordon kind of thing, and you get the inverse of this thing. What is this structure? What is this phi h c? Is it local? No. Phi h c is a non-local object. Okay. So what I am calculating gamma effective here, it's a non-local effective action. But what I am writing here, it's a local effective operator. That means I have to reduce this non-local effective action into a local effective action. And I can do that. Why? Because I know that non-local effective action or non-local structures are nothing but an infinite sum of local operators. So I can perform an expansion over this del square by m square, like a binomial expansion, okay? And I can write down the infinite number of operators, and those each operator in the infinite expansion are the local operators. And now you can see that you start with a dimension, because phi HC has a mass dimension 1, but what it will generate? It will generate all infinite operators having mass dimension up to infinity. And why I can perform this expansion? Because I need to know whether this expansion is convergent or not. And that's where exactly the decoupling and the effective field theory notion comes into the picture. What is your del square? If you go to the Fourier modes, this del square is nothing but the p square by m square. What is this p square? It's the on-shell momentum of the particle. That means when you perform some kind of process calculation, okay, I remove that. So this is, let's say you are calculating this phi L, phi L, phi L, phi L, and this is your phi H. What is this momentum? That momentum is basically the on-shell momentum of the phi L passing through a S channel of the phi H, right? And that momentum has to be very small. Why? Because if the momentum is very large compared to the phi H mass or more larger than then of course you are producing phi H on shell. And if you are producing it on shell, you cannot count it as a lighter degree of freedom. That I can do only when it is counted as a heavier degree of freedom, that I cannot produce it on shell. So that tells you that momentum transferred, this p square must be much less than your m square. So if I can, that means this expansion I am performing to the power n, where n goes from 1, 2, 3, 4, 5. So you can see p square by m square is larger than p square by m square whole square, right? And if you see, the operators associated with them are basically of different mass dimensions. Now when I am performing this expansion, that's where the effective action transformed into a local collection of the effective operators. Okay, so that's why the locality and non-locality, these understanding are very important to understand the effective field theory. When we talk about the effective field theory, we talk about the local operators. Okay, and so we'll see that when we integrate out, there are certain things we have to keep in mind. For example, what about the gauge invariance? Because my theory has a gauge invariant. At the low energy, I have a gauge invariance. But in the process of the integrating out, if I lose the gauge invariance, then I lose basically the, one of the interesting property of the theory. And if you lose the gauge invariance, the renormalizability and many other beautiful aspects of the theory are lost. So it's not only my duty to integrate out, but also we have to integrate in such a way that my gauge invariance is protected. Okay, and that's what we learned is something called the covariant derivative expansion. You have seen the word covariant derivative? Where? In the gauge theory context, right? So you upgrade your del mu phi to a d mu phi such that your d mu phi and the phi transform in the same way, and you can protect your gauge invariance in the theory, right? So we'll learn how to perform this expansion, but still it's not the full story, because when you do this thing, that's the tree-level propagator. But this is not all. For example, let's say I have this kind of one loop diagram, right, where it consists of heavy propagators. So this also I have to perform an expansion of this in this propagator because if I calculate this one, this is a non-local effective action. So this one loop non-local effective action also I have to reduce in a consistent way in terms of collection of the local effective operators. Okay, there are more trouble. For example, if you have this kind of thing in the loop, one particle is heavier, one particle is light. So you cannot just reduce them. You can make them shrink. For example, when I am performing that expansion, diagrammatically what I am doing? I am actually generating these operators. Right? Because all are basically local operators. So this non-local operator reduced in terms of infinite set of local operators of different mass dimension. That's what you are doing. But this diagrammatically, if you think that in the real space, this is x, this is y. Now, when I'm performing that expansion, what does it mean? You are taking the limit x tends to y. So if you have a Green's function, you propose just a Green's function gxy, you are taking the limit x tends to y. And how you take that limit, that's what actually performing that expansion. Okay. So now when you perform that limit, similar limit you can take for this propagator, but this light propagator is light. So you cannot perform the same game there. But that means that particular, this kind of diagram where in the loop you have a light particle, heavy particle both, you cannot reduce it completely in terms of local operator. It is a combination of local and non-local. But I am interested in the local part. So I have to understand how I can extract the local effective part from there. So I have to extract the local part, and that will be contributing in my effective Lagrangian when I am writing. So these are the all captured in the method that I will be discussing in this class, which is called the heat kernel. Okay. I will not go to the functional method and all those things because the functional methods are not a complete. There's a lot of mathematical glitches are there. So the mathematically consistent, perfectly fine working theory, and it's one of my favorites. So I'll discuss the heat kernel method, how to use the heat kernel method to integrating out, fields and all those things up to one loop and so on and there. Right. And now the third point is basically the unfolding. What does it tell you? It tells you basically, let's say, as a bottom-up approach, you add, as I told you, from the experimental point of view, that okay, if I rely only on the renormalizable interactions, I cannot just explain all the data. So I have to add classified dimension 6, dimension 8, depending on what kind of observers we are looking at. We add those operators. Okay. But now let's say we add those operators, we perform the fitting and all those things. There are a lot of new methods that are coming in, ML and AI, whatever, Bayesian method. Okay, but at least we know the size of those Wilson coefficients from the fitting. Okay, this is the size of the Wilson coefficient which can explain the data beyond this thing. Fine. So your experimental colleague give you, okay, for this operator, if you fit against this operator, this is the size of the Wilson coefficient. But that is not the complete story for searching for new physics, because at the end of the day we need to know what is the new physics, what we get through the effective field theory. From the effective field theory we get if there is some new physics that is captured with them, but what is it exactly we do not know yet, right? So that's what the unfolding does. What does it tell you? In a symmetry driven way, just you do the reverse engineering from right hand side to left hand side. Now you have a x tends to y limit. Now you separate out x and y, they are unequal. And you try to see, because these are the asymptotic states, so what are the symmetry of the asymptotic states? Such that, because remember, when you write down this kind of diagram, what are these? These each vertices are basically singlet under the symmetries. Whether it's a space-time, whether it's a global, whether it's a gauge, whatever. Whatever symmetry you have in your theory, each vertex has to be singlet under the all and individual symmetries. Now using the representation theory, if you know the quantum number or the how do they transform or the representations under those group, you can say what are the possible quantum number or the representations of this guy. Right? This may not be unique, but at least you know how to minimally extend that object such that you can construct a minimal UV theory. And why is it useful? Because if you do not have that, then you just blindly hunch for new UV Lagrangian, you try to integrate them out and try to get the see at the low energy whether you get the operator or not. But this is symmetry driven mechanism to tell you what are the minimal UV interactions upon integrating out generated this kind of operator. Okay, so this is called the unfolding. So it's like a experimental, you take experimental colleagues input and then you get the size of the Wilson coefficient, you unfold that operator, and that unfolding can give you, okay, 3 or 5 minimal extensions, and you find out, okay, 3 and 5 different kind of UV theories, right? And then from there you can calculate, okay, what are the possible way, you can discuss those UV interactions, what are their quality among them, what their mismatch and all those things, but it's a guiding principle for the UV interactions.
You are trying to constrain the UV theory using the
Yes. So now, sorry.
get some information about the UV theory from it.
Yes. So what are the minimal way to extend the low energy theory such that you can do that thing? Okay. Any question?
So, when you write an effective field theory, like, do you make any assumptions about its higher UV completion? Like, for example, say if in the top-down approach, the theory that you start with, does it have to be perturbative or can it be non-perturbative?
No,
as
no.
well?
So all are hidden here in this thing. If your theory, heavier degree freedom, satisfy the decoupling limit,
Yeah.
okay, you can do the EFT expansion. And to satisfy this decoupling limit, all the qualities have to be respected.
Okay. No. So just like a naive question, if
Yeah,
I have,
for example, if your UV theory itself is not renovable, what is the point of doing that?
I was thinking if it's non-perturbative, say QC at low
Non-perturbative, no.
temperatures.
So basically, that the truncation will not valid. Then for the non-perturbative, how do you define the decoupling?
So it doesn't make any sense to write a effective field theory for that non-perturbative
Okay,
theory.
so there is a way to do that. I mean, the low energy QC, you can do that thing. Yeah, one of our experts, Otonu, is here, so he can talk about those things. But that's also certainly in certain momentum regime, you can do that very specific way. It's not a very global way you can do that thing, that across the regime, this thing. But yeah, so what I'm calling about the effective field theory is mostly for the high energy and low energy theory. But there are certain class of, for example, soft coronary effective field theory, chiral partition theory and all those things, chiral chi-FT and all those things. They require special attention for that, where the composite where the objects are not fundamental even. For example, if your Higgs, let's say, is like a pseudoscalar, it's a bound state of psi bar psi, then this kind of formula need to be upgraded accordingly, bottom up and top down, everything, but can be done. Okay. But what I will be discussing primarily, the objects are basically fundamental degree of freedom.
Okay, so we other than that, we do not really need any other assumption about the UV completion.
Yeah. If the theory is renovable, I mean, it's a well-behaved UV theory. It has a unitarity and all those things. Okay? Yeah.
So I used to think that the reason why we got so you start with 5-4 and you go to higher loops and you see that it diverges. So you can think of you think of it as adding new operators to your theory, or you say that these loops generate new terms in your Lagrangian, in the Wilson effective Lagrangian. I used to think that this arose because of the fact that this theory was an approximation of a full UV theory, which would be the theory whose Lagrangian is described by all the terms that we generate.
No. So thing is basically there are two things. One is basically, if I understand correctly your question, your UV theory, let's say I start, as I told you that, okay, my preferred UV theory which is renovable. So I have a UV theory which is renovable. I can write down an effective theory which is also renovable automatically to me. So if I add those operators, even if I do not add those operators, I don't have any issue of the renormalization. For example, if I have a 5-4 theory, I can renormalize that theory, but I will generate some more operators additively. Right? For example, I can write down the 5-6 terms using the loops and all those things. But that is certainly not a 5-6 local operators. For example, let me tell you this thing. For example, let's say I have a phi cube interactions in my theory, okay, and then I have these, I can calculate this process.
And this will give me a phi 6 operator. Like
Non-local, but this is non-local, okay. But when I'm saying a phi 6 local operator, that is not this, that is this one. So in the Wilson effective action, you get this. You don't get this until you do the effective. That is the difference between non-local and local.
No, but can I think about, so I can write the most general Lagrangian that is allowed by the symmetries.
For a with the given degree of
See, I
freedom.
have Z2 symmetry and all the symmetries.
For a given degree of freedom.
Yeah, and I can write this general Lagrangian which has phi 6 derivatives and all these things, and that is basically what I generate when I do loop corrections, right?
No, that's
you generate everything that is allowed by the symmetries, basically.
Yes, you generate everything.
Can I think of that as coming from a higher theory which I have integrated out?
Not necessarily. Not necessarily. For example, if you do from the loop correction only, that is be dictated by allowed by some kind of symmetry. So that is not the correction you add. So if you have to add an effective operators for the given symmetry, you have to use this approach. Wilsonian approach doesn't give you that thing. You have to use the Hilbert series approach to, for a given symmetry and given degree of freedom, I construct all the local operators. That's the Hilbert series, the bottom-up approach. What Wilsonian EFTs does, you start with the UV theory, and you basically, so basically your integration limit is basically 0 to infinity. You truncate that 0 to lambda, lambda to infinity, and all the modes between lambda to infinity that you are integrating on, the path integral, right? But if you integrate out all the frequencies or all the modes between lambda to this thing, then you generate this kind of non-local effective action, what I am calling this thing. But still it is far away from writing the effective operators. Okay. So those effective operators will be generated only when you replace the heavier field by its classical solutions and you perform a non-local expansion over that, then you generate those effective operators.
But one last question. You wrote that, you drew that diagram, and that has a divergence in phi 4. If I start with the phi 4 Lagrangian and try to calculate the amplitude for that, that will give me a divergence.
For phi 4, interesting.
Yeah.
Yeah.
And then what I do
I
is that I
theory.
add a phi 6 operator.
No, why do I add this thing?
No,
if I have phi 4 theory,
renormalization generates a phi 6 operator that corrects
but that phi 6 operator will be finite. If I have it, if I'm working a 3 plus 1 dimension, if I compute this diagram, this will be finite.
A diagram like this, that is divergent.
What do you mean the diagram like this are divergent?
This is convergent for phi 4. This diagram.
No, phi 4 will have a divergent part because it's the marginal operators and relevant operators. If I add a hard, for example, so all the other hard dimension operators when I generate, that will, why they are divergent, I don't understand.
No, I am asking if this diagram that you have drawn here is divergent if I calculate this with the phi 4 Lagrangian.
If this diagram is divergent when calculating
in a phi 4 theory.
In a phi 4 theory. Okay, so let's try to see what kind of diagrams you can have. So if I have a phi 4 theory,
That diagram.
how do you draw a phi 6 operator there?
So one sides and one cross.
No. Okay, so this thing and then this thing, right? Yeah, so why this is divergent?
No, I'm asking if this is divergent.
No, it is not, because you can just naively think these are 3 propagators are there. So D4 k by k6. So the thing is basically you can just keep in mind a very naive way, it's a superficial way of understanding. If your renormalizable theory, writing up to lambda phi 4, all other operators that will be generated, they are actually non-local operators. Okay, and they are actually finite because you don't have any counter term to add in your theory. But if your Lagrangian contains, let's say, lambda phi 6 operator to start with, then when you renormalize them, then it will be divergent. Because then I have a counter term corresponding to that to cancel. So if my theory is renormalizable, okay, and then if I have a certain up to, let's say, O operator, and I generate any other operator additively which are not present in my bare Lagrangian, has to be finite. Otherwise your theory will not be renormalizable.
No, I was trying to think what diagram would give a phi 6 type correction.
What diagram gives you phi 6 type? Like
In-
this kind of, if a phi 4, this kind of corrections diagram will give you the phi 6 correction, but this is a convergent diagram. This is finite. In a large asymptotic limit, just say 1 by k6. Author can tell you the number even. He is an expert on loop calculation. Right? D4k by k6. Even you do the cutoff, naive cutoff, it's 1 by lambda square. But what I am saying that this is not giving you the local phi 6 operator. It's a non-local operator. Okay. Okay. So we have half an hour time. So we are okay. So I will not go too detail because I will anyway come back to all these things. So the unfolding is basically when the experimentalist give you an operator, let's say, because they perform a fitting against, because your scattering amplitude and all those things observables, and not only renormalizable couplings but also the Wilson coefficients are also there. So their cross sections, everything have that, right? So when you perform the fitting, you see get the numerical range of those size of the Wilson coefficient. You get that thing. But next question you want to understand, what are the possible UV theories from where if you come down, you can still explain the data. That will now the next basically how to hunch for the new physics. So this is a symmetry guided way to look for new physics, that you unfold that thing in a minimal way, because if you allow the non-minimal, you can draw thousands of models. Okay, there's an unbounded thing. That's what I'm saying. The minimal extension, if you do, you will see there are 4 or 5 different new physics are there, and from there if you come down, that means all these new physics can explain the data, but if other new physics in a minimal way cannot explain the data. So you can create a statistically favored model based on this kind of thing. This is just a way to understand the exactly, yeah.
There,
Because your Lagrangian, you are working the local Lagrangian. That's why I'm working. So if I have to add in the Lagrangian, I have the local operators. Yeah. There are physics and field theory of non-local Lagrangian. That's fine. But what I am interested in the local.
there's no relation between Wilson coefficients and running couplings.
There is no.
You are saying that there's no relation between.
No, I am not saying that.
There is.
Yes, of course, because the Wilson coefficients, what are those Wilson coefficients? Wilson coefficients are function of those BSM, UV parameters. Okay? So now the Wilson coefficients, when they run, of course, they are running and induced to the running of those operators also, because Wilson coefficients also run. When you have this Wilson coefficient, it's not like they are scale independent. There's something called the anomalous dimension matrix. Okay? Using them, you run the Wilson coefficients. It's not the renormalizable couplings run, the Wilson coefficients also run. Now, when you come down from a higher theory, for example, I can tell you one example. Let's say I have a UV Lagrangian, which is, I am just primarily focusing on what is required, lambda h phi h to the power 4 and plus lambda LH phi L square phi square. Okay, so this is the Lagrangian, UV Lagrangian I have. Now when I am integrate out the phi h, what I get some Wilson coefficient as a function of lambda L, lambda h, lambda LH. So now the scale, these are scale dependent. So now when I do the UV calculation, what I'll do? I do the running of lambda L, lambda H, lambda LH, and I come down at some scale, or at some scale I have some predictions. Or if I look into the effective field theory point of view, I have C and lambda L, because lambda H and lambda LH are no more. So what I'll do? I'll do the running of C and lambda L, and through the matching I know exactly how the runnings are related to each other. Okay. Okay, any other question? Fine. So these are the broadly, three complementary topic of effective field theory, which actually gives us the understanding the high energy physics from an effective field theory perspective. Okay, and our task would be to discuss these in great detail, and all the assignments, exam and everything will be basically based on this thing. And what I am going to cover initially, whatever I discuss, the integrating out, the operator constants and everything at 0 temperature, T equal to 0. So I'll complete all the tasks at T equal to 0, and then I'll do everything in terms of finite temperature. Okay, that unfolding, top down approach, bottom up approach, integrating on everything I'll discuss in the finite dimension. Fine, but any other question before I proceed up to this part? Yeah. Hmm.
Starting from lower order operators, but the theory is non-renormalizable.
No, okay, very good. You have raised this question. So the thing is, it was a very primitive idea initially when the effective theory was being discussed, that effective field theory is not renormalizable. But that is certainly not true. The reason is basically you have to redefine the concept of renormalizations in the context of effective field theory. So when we are truncating an effect, for example, what is the meaning of effective field theory renormalization? That until the phi 4, you extend your theory to phi 6, let's say. Okay. So for example, I add, So let's say I add an operator C by lambda square phi L to the power 6. Okay. So if I add this operator, then what I'll find out, additively I'll generate more operators at the dimension 6 level itself. So when I'm going to renormalize the theory, I have to make sure that I list all the operators up to that dimension order. Okay. That means it is not only the phi L6, but it's all CIOI6. So I add a complete set of non-redundant dimension 6 operators. Then what I'll find out, that all the divergence associated with the dimension 6 operators, I have a counter term for that. And on top of that, as Siddharth has pointed out, I may generate some kind of lambda 4 operator counter term. But I will be ignorant to that. Why? Because initially I have already truncated my theory at 1 by lambda square. So anything beyond 1 by lambda square, I will not be paying any attention. If I want to pay attention, then what I have to do? I have to add lambda 4 Ci tilde OI 8. Once I add them, then I am allowed to do that thing. So basically, first you have to decide what is the definition of your effective field theory. If your effective field theory definition encapsulates only the dimension 6 operators, then we will write down all the counter terms up to dimension 6. Whatever beyond dimension 6, I will allow. But if I write down my effective field theory up to dimension 8, then of course I will get the not only dimension 8 counter term, but also some dimension 6 counter terms also participate to cancel this thing. That's why when you calculate the dimension, go to the higher dimension, the lower dimension operators, the product give you the counter term for that thing. Okay. So so effective field theory is also renormalizable, but order by order.
Yeah. I think he was pointing towards that point, like from dimension 6, then you can.
No, so I think his thing was really, if you have a 5-4,
5-4 on.
I don't generate a 5-6.
That on.
I generate a 5-6, but that is not a local operator. You have to add a 5-6 there, and then you generate 5-6 operator counter term. So all other operators will be finite in that sense. Yeah.
So using the dimension 6 effective Lagrangian, so my question is, using the dimension 6 effective Lagrangian, if we calculate suppose a dimension 8 non-local diagram, then it should be finite.
Yeah.
Yeah, but
No, there will always be non-local contributions, and that is finite. The finite part is, so we are worried about basically what are the counter terms to cancel the counter terms.
Okay.
So if I might starting series is basically up to 1 by lambda square. Why do I bother about anything divergent or finite beyond 1 by lambda 4, 1 by lambda square?
Yeah, but that dimension 8 operator that you are talking, that.
So if I want to cancel those counter terms, in my bare Lagrangian, I have to have the dimension 8 operators. So that's why it's called the order by order renormalizations. Yeah.
So, like, if we have multiple such fields that we are integrating out, what should be the power counting? Like, will we have multiple power counting parameters in that sense, like M1,
You know
M2?
how to integrate out non-degenerate fields.
Yeah.
So that's the result. And
But
the
then
scale is
mixing
basically the
as well.
lightest heavy scale. Lightest heaviest scale is basically chosen to be the cutoff.
90 degrees.
But other scales are also involved.
And we can write an expansion with
Yeah.
2 scales as well.
Yeah, exactly. Siddharth.
So at
In the unfolding. Yeah.
so we have some EFT and at some
Hmm.
So we go back to the unit. We have an exact unit for that because we have
No. That's what I'm saying, that when you unfold, even for the minimal extension, you have a variety of theory. Right? You have a variety of theory. And so variety of theory in the sense, if you think about just a tree level, just a simple example let me give you. Let's say SU2 doublet, or something like, okay, let me call it. Let's say I have a SU2 triplet scalar. Now, what are the possible choices I can have? This can be 5, 3. 1 I will not take because singlet, so but yeah, let's take singlet also. Because 3 cross 3 give you 5, 3, 1 in SU2. So that means this guy can be a scalar of under SU2, the representation could be 5 dimensional or triplet or singlet. Okay, so that you can see 3 different theories. And being integrated out, all give you the same operator. But at least you know what are the 3 theories. If you do not use this mechanism, you just look for any arbitrary random UV theory and try to see after integrating. This gives you the belief you will get the operator even before performing the integrating out.
three UV theories from corresponding these operators will be the same operator.
Exactly.
The other maps
Exactly. Yeah, I'll come to that, and much more some interesting properties are there. I'll discuss it. But this is the basic idea of what is the unfolding implies. So, in the effective field theory, when you add those effective operators, okay, so you just add them order by order. For example, you add dimension 6 operator first, then dimension 8 and so on. Right? So, for example, if I add only one dimension 6 operator, okay, that means I can have only one counter term to cancel that thing. But what I'll find out, I generate more interesting other kind of dimension 6 operators which you have not added and which are allowed, but they are divergent. Okay, so that means that you cannot cancel their counter terms, divergences. So that's why when you have to renormalize the effective field theory, you have to add a complete set of operators initially. Okay, and that's why I add a complete set of operators. Now what will happen? Whatever the dimension 6 operators appear that belong to this set, because this set is complete and exhaustive, so there is no lack of having counter term to cancel those divergences. Okay, So that's why now I can say I can write down my effective Lagrangian up to dimension 6 and I can renormalize effective Lagrangian up to dimension 6. But there is certain more than that. Here when you do this calculation you can generate some dimension 8 operators which are basically divergent. You have a counter term but you don't have a counter term to cancel, but that's fine because you start your Lagrangian, effective Lagrangian up to dimension 6. So whatever 1 by lambda square is important to me, anything whether it's a finite or divergent beyond 1 by lambda square I am not worried about. If I have to worry about divergent term associated with higher dimension operator, I have to add that operator in my bare Lagrangian. So if I extend my bare Lagrangian beyond dimension 6, I add the dimension 8 operators, I will have a counter term for all the dimension of 8 operators, then I will this thing. But when you add them, you generate the divergences which are of the order of dimension 10 operators. So that's why the renormalization for the effective field theory is order by order. That I truncate first and I say I am interested in dimension 6, I will renormalize my dimension 6 effective Lagrangian, and whatever is there I am not worried about, I just throw them because they are not going to affect my theory. So concept of renormalization is slightly different than the usual UV renormalized theory, because there when you start a UV renormalizable theory you add the counter term and you go to any loop order, you don't generate any new counter term, right? Because if your theory is renormalizable. But here also the same thing, if you add a complete set of operators and order by order renormalization, that play the same game.
That complete set of order operators is finite.
Exactly. And that is what is the number this method tells you. The dimension 6 level, dimension 8 level, what are the number of operators, that method tell you how to count that thing, because that depends on what is your degree of freedom and what are your symmetries. Okay. Okay. Any other question? Okay. So now there's another important aspect about the effective field theory that I'll discuss. So, class is till 12, right? So about the choice of the renormalization scheme. So how many of you are familiar with the renormalization schemes? Are you familiar with renormalization schemes? No? Okay, so then, yeah, then brush up. So what are the renormalization schemes?
You have different, you can define different type of subtraction schemes.
Yeah, but can you name some?
MS, MS bar.
MS and MS bar almost same. Yeah.
Polyvillars, dimensional.
Polyvillars is not a good one.
That's
Remove
not
that.
That's a regular regulation.
On-shell renormalization scheme? Huh? Off-shell momentum subtraction?
Moment.
Off-shell
MOM.
off-shell momentum subtraction. Okay, you don't know.
What is MOM?
Yeah, I am going to tell you what is that. So now in the effective field theory, we have to understand that when we do all this loop calculus and all those things, we choose a perfect renormalization scheme. If we do not choose that, we may end up having nasty results, and we cannot explain the decoupling. For example, if I have a just blindly use MS or MS bar, of course I am not going to discuss this renormalization scheme, you just read it by yourself. So what we do, we look for 1 by epsilon part, right? And we subtract that thing. From there we define the renormalization constant, and from there we calculate the beta functions. Now let's say I have a theory of having two masses, small m and capital M, okay, where m is much greater than m or m is much greater than m. Okay, these are the hierarchies are there. That means if this is the situation, then I want to decouple my theory, this field from my theory, okay, or if this is the situation, I want to decouple this one, okay. But interestingly, in the renormalization scheme, if you use the MS and MS bar, and if you calculate the beta functions, they don't depend on M or N. For example, just think about this way. You calculate, okay, is take a QED, so I take a QED, and this is my fermion, and this is my mass of the electron. Okay, you calculate the beta function, and your beta function will not depend on the mass of the electron, or also if I have some kind of scale involved in my theory, the beta function is a scale, the floating mass scale independent, and that is some kind of troublesome in the context here, because when I'm trying to decouple a particle, that particle is not, should not contribute in my beta function if the particle is decoupled. But if my beta function doesn't depend on that mass, then as you can see, whether the M is there or not, or is it decoupled or not, that information is not captured in that beta function information. So beta function is immune to this kind of hierarchy, right? So that's why if I have, so the notion of the decoupling is actually missing from this MS and MS bar kind of scheme. But what we can do, we can think of other scheme which is called the off-shell momentum subtraction. There we get the notion of this thing. So let me just see the numbers now. Yeah. So if I calculate this diagram, this is the M, is the P mu momentum is going there. So I is square by 2 pi square P mu P nu minus P square delta mu nu, sorry, yeah, eta mu nu, and then 1 by 6 epsilon minus gamma by 6 and then 0 to 1 dx x 1 minus x log m square minus p square x 1 minus x 4 pi mu square. Yeah, right. So here I have used dimension regulations. So this is what actually, if you calculate the diagram, you get this thing. Now I use p square equal to minus m square, okay, and if I do that, then I can calculate the beta function by using e by 2 m ddm. So what I'll do, I choose this off-shell momentum subtraction, p square equal to minus m square, and then I'll find out the coefficient of this e square p nu part, and then I'll add this operator. So this is just a Kalan-Simanjik notion of how to calculate the operators. So basically look at the coefficient of this part actually, okay. So then your beta e in this definition is minus e by 2 m dt m 0 to 1 dx and whatever you have, yeah, you put that thing. And if you calculate that beta function, what you will find out is the following result: e cube minus 2 pi square 0 to 1 dx x 1 minus x m square x 1 minus x by m square plus m square x 1 minus x. Okay.
So that is p square equals
Minus m square. M is some scale. Yeah.
small m is the
Mass of the electron.
and e is the
Where is the mu? No, this is,
there's no mu.
yeah, this is the dimension regulation, this scale. M scale. Okay. So now if you calculate this thing for m much less than m, what will you find out beta E? Just calculate, this is a simple calculation, E cube by 12 pi square. Okay, and if you calculate m is much greater than m, what will you find out beta E as E cube minus 60 pi square m square by m square, which basically tends to 0. So you can see the beta function actually changes when you have this mass hierarchy between small and capital M. So if you plot this, what you get is the following. If this is 1 in the unit of 12 pi square by E cube, it actually goes asymptotically to that number. Okay. So if this m, that means the particle which is floating inside the loop, okay, is much heavier than some kind of choice of scale m, then this beta function goes to 0. That because why? Because that particle is not there to contribute even in the beta functions. Okay. So when you calculate the beta functions, they are basically on shell degree of freedom which contribute there. If the particle is not produced on shell, that should not contribute. But if it is scale is much larger than this thing, then you get perfectly mass independent one. So that tells you if you make the electron mass to be very heavy gradually, at some point it will be decoupled from your theory and it is not going to contribute in your beta functions. But if you use the ms bar, what you will get in the ms bars or ms scheme, you get exactly the beta E equal to E cube by 12 pi square. In that beta function calculation, in that scheme, doesn't have the notion of the decoupling because it's just independent of your mass. That's why to understand the decoupling, one has to use this mass dependent renormalization scheme. Now the question is basically, these schemes are not very useful when your lighter particle is massless. Okay, because then a lot of issues appear. So we have to go back and then use the ms and ms bar scheme, which are very useful schemes. But then how do I implement that? That's where the effective field theory come into a picture. So first you have to see, if already you know that m is much greater than m, you first integrate out the electron from your theory and then you calculate the beta function. Okay, because if you calculate mass of the electron, m is basically some scale of the theory, just to say that electron is decoupled or not with respect to some scale.
That decoupling happening at the that image, small image, right? Because
Sorry?
mass of the electron is there.
So you can choose capital M and mu will be the similar.
Yeah, exactly.
Okay.
And decoupling,
But I just remove mu and m to say that, okay, if there is some new particle is there, let's say, that is not part of the mu but part of the m.
part of the aim.
So basically now let's say, so basically why I introduce the capital M, because you can generalize this thing. If you have two particles, you calculate the beta function with two particles and then you make one particle is very heavier than other one. So the beta function should change. So just to capture that effect, because if you mark that capital M and mu is the same, you cannot do that game. So you can think of this way, na? So basically you start with, let's say, two particles, okay, and then you put one particle is very heavy, then the other one which is decoupled.
But then you have the other diagram, because you don't have any heavy massive diagram. I mean, a heavy particle there.
Yeah.
So you have only this.
No, you just
particle like
you just cumulatively add that contribution. That's why the m square comes into the picture. If you have same diagram with a different kind of m.
Because I don't know what is capital M mass for.
So basically, okay. So this is a basically you can think of some kind of an off-shell momentum. Okay. To start with, it's an off-shell momentum. It is, let's not associate with some kind of particle mass. Okay, but
This one with this mu.
mu is the renormalization scale coming in the dimension regulations. But this is just another off-shell scale you are choosing. So this is not an on-shell choice. Okay, and now within that moment, within that off-shell scale, whether your electron mass is heavier or light, that's what you are trying to understand.
So that scale is coming from some new particle, that new particle.
Yes, you don't know. You just, so that's the notion of the off shell, because on shellness, if I have an on shell subtraction, like an on shell scale when you do, there you have to match up with p square equal to m square the on shell condition.
I see. Then depending on this scale, so you can generate that one.
Exactly.
And or you can
If,
have that field.
if you go to the on shell limit, you generate that particle. Otherwise, you are always off shell. So that's why it's called the mass dependent scheme. Okay, okay. But then in the effective field theory context, that's why it suggests basically that if you know the particle is going to decouple, you first decouple that and then you calculate the beta function. If you want to use the MS or MS bar scheme, because always we use the MS bar scheme because that is the most reliable schemes we have. But to use the MS bar scheme, you actually have to be careful that if the particles are already in the decoupling limit, you first integrate that out particle and then with the theory you this, because then not only the renormalizable Lagrangian but also the effective operators also run and all those things in the MS bar and all that will capture that effect. But if you do naively, that kind of mistake you can get, because that notion of the decoupling is absent in the MS bar because it doesn't have the information about the mass of the particles. Yeah.
For UV, you are saying that we should take a off-shell subtraction. Only then you will get the beta function dependent on the mass.
No. What I'm saying that if you have to understand the notion of a decoupling from a theory, okay, then unless you decouple that particle initially, okay, you calculate the beta function a prior, okay, and you try to understand how the beta function behaves with respect to the decoupling, then MS bar is not a good scheme because MS bar doesn't give you that flavor of decoupling. It's immune to that hierarchy between capital M and small m. So off shell subtraction is a scheme which actually have that hierarchical dependence and give you the notion of the decoupling, because you can see that how it behaves, because this is just a m by m, it's larger than something. Okay, so but in the MS bar, but you want to use the MS bar scheme for several reasons we will discuss later. Now how we can use? First, I will, if my electron is very heavy compared to off shell momentum, okay, then what I'll do, I'll integrate out electron from my theory. I'll have only photon and some effective interaction of photon, and I'll calculate the beta function of that effective operators and the renormalizable operators.
In this part, when you see that for in this part, you don't have like you have to integrate out the
Exactly. I have to construct the effective field theory first, and then I will calculate the beta function.
then you have the intent of decoupling.
Exactly, because then I have the Wilson coefficient which have captured the running and everything there.
So in both ways you can get the same.
No. So Wilson coefficient, when you do the run, then the decoupling information is there actually, because you have already decoupled that theory. The idea is basically whether beta function has the information of the decoupling or not, how to capture that. That is the discussion I'm going. So if decouple, use the MS bar scheme, or if you don't want to decouple and just from the raw beta function you want to get the filling, you use this defined scheme.
In both ways we can get
You get the idea, but in real practice, when you do, you will understand that we cannot use this scheme in a very natural way. A lot of issues are there, but MS and MS bar is the best scheme for us to, with a lot of degrees of freedom basically massless. Yeah. Okay, so today I'll stop here.